Thanks for being here. Thanks for the wonderful workshop we're having. It's pretty amazing. So yeah, this is where we did the last couple, more 3 years, with many people, as you see there. And there are many words there in the title. There is AMG, there is filtering, there is contact, there's optimization. So many components had to come together. And Tucker already gave the talk on the interior point optimization, which we do use here, and he did help a lot in the development of that. Sanio and I worked a lot on the solver that I'm going to present, and Mike and Jerome from engineering more on the contact side. Eric helped us a lot on Tribal. Tribal is a library based on MFEM that will provide gap and Jacobian for contact. And then Cosmin led the project. So this wouldn't be possible without all of them. Okay, so the goal was to do large-scale contact mechanics under optimization, and we're going to use the IP method for the optimization because we had Tucker and he was the expert. Also because, as we're going to see, it will demonstrate mesh independence convergence. And we realized, and I will demonstrate, that we needed a good preconditioner for these systems. And it doesn't advance. Okay. But let me give you the setup first, the formulation. So under contact, we have two bodies, and under these maps will be deformed into contacting states, and they will meet in some common interface. Let's call this gamma C, the contact boundary there. And there are more than a couple of ways to define the contact. In this work, we use the mortar method or the segment to segment because of being more robust. And this is also in Tribal, was readily available to us, where you define the gap in this weak sense. And the objective here for the specific case of frictionless contact, you can define your problem by minimizing this energy functional, where in this case I'm using linear elasticity, but it might as well be nonlinear. I will also show an example of that. So if you discretize with finite elements, you end up with something like this, subject to the gap function being non-negative, meaning you don't have penetration of one body to the other. And here we also use linearized gap. So you see the Jacobian here of the gap function around some reference displacement. So if you use the interior point solver, you replace your inequality constraints that are coming from the gap to equality constraints by introducing those slack variables. And then interior point solver, as it was demonstrated in the previous talk, will solve this family of regularized log barrier problems as you in the limit where mu goes to 0. And under some tuning and scaling of this mass matrix, you will see that we achieve mesh independence convergence. So in practice, at every optimization step, you have to solve this 3x3 system. U is a displacement, S is a slack variable, lambda is a Lagrange multiplier. And if you reduce the system only on displacement, you will end up with a system that looks like this. K here, in the case of linear elasticity, is just the linear elasticity stiffness matrix of the two bodies, or more than two bodies, doesn't have to be two. J is the Jacobian of the gap function, and D is this log barrier Hessian, which becomes increasingly ill-conditioned as the IP converges. As you apply more and more the contact constraints, this D becomes terrible, and it ruins the whole system. So let's look at our example here, like a very basic one. We have a cube resting on this beam, and it's pushing downwards. This one is fixed. This is the final configuration. Nothing fancy here, but as you can see, how the solver is behaving, like AMG on this system, as you converge. So basically the contact constraints are satisfied more and more. AMG suffers. It goes from 100 iterations to more than a couple of thousand. Now, if you take a closer look to the system, within the iteration, within the optimization iterations, K is fixed, J is fixed because we use linearized cap. So J is fixed, K is fixed, only D changes. So this is all D's fault. So, and you could, with it, yes, I will show you. Yeah, exactly. So this is AMG, this is what D is doing. So you could see the relation between what's happening. But as it was pointed out just now, D, the size of D is just the number of constraints, it's diagonal matrix, number of constraints, and J is highly sparse because J has non-zero rows only at the dots where are adjacent to contact or they are affected by contact. So this is really small compared to the elasticity dimension, the dimension of the displacement. So if we filter out that subspace, this is what happens. You recover the robustness with respect to the contact constraints. And I will show what we mean by filtering out. So we need something to take care of the subspace that's causing this issue. So let's formalize everything a bit. So if UH is my solution space, let's say I have two bodies now. Again, it could be more than two. And consider the basis. And then the contact subspace is really the dots that you see there, like on the touching surface. So if we define WH to be the span of those shape functions that they have support in that area, and we define the U and W, the corresponding discrete coefficient space, really. Let me define another couple of operators. P here will be the embedding or the algebraic or the matrix representation of the embedding from W to U. And then A will be the system in the whole space, and AW will be the system on that subspace. And let me define also this space, which be the orthogonal, the A orthogonal complement to the range of P. Okay, I'm getting a bit technical here, but that's it. So I have P, A, and my V here. V basically it's the space that there is no contact. You can think of it this way. Then under these two assumptions, we can show norm equivalence. What are these two assumptions? Let's say you have a solver on subspace U, which is convergent, not normal equivalence, just convergent solver on this big space U. And then you can show normal equivalence in this orthogonal complement. In our case, it's like the space that contact is not happening. Then you can show that this multiplicative coupling of solver, and in the middle this correction, then you can show that you can get to an estimate that is, you can show norm equivalence of this preconditioner M with the inverse of A. And I bet many of you see this and you say, oh, I know this, and I know these assumptions, because yes, it is related to subspace correction when we do multi-grid, when we do multi-level. But in this case, a bit special about contact because the spaces are not like nested grid. It's just subspace that the contact is happening. So let's see how the proof is done and outlined. It's the standard way we do these proofs. So we have to really show two bounds. Usually the lower bound is the easy one. You bound your inner product derived by the inverse of the preconditioner with A. This is usually easy to show. More complex would be the upper bound, which usually you have to come up with a stable decomposition, and we are able to do this. And along with the Schwarz lemma for additive Schwarz, you can combine all this and you prove this relation there. Now in practice, let's see what this means. You could make B here. In our case, we will use AMG because it's elasticity. And we can make this be convergent with just omega equals 1 using L1 smoothers, for example, which are convergence for SPD matrices and everything. And what is this beta? Beta is the condition number, really, of the precondition system with AMG in the absence of contact. So what this tells us is, if I solve the problem with AMG, if I didn't have contact, then I add contact in it, then the worst it can happen is like I can roughly double the condition numbers. So the number of CG iterations, they will roughly be multiplied by square root of 2 in the worst case. So no contact, I have a specific number of iterations. With contact, the worst thing is multiplied by square root of 2. So we can have an estimate of an upper bound of what will happen. So let's go back to the first example I gave, which in this case, little detail here, we also do some pseudo time stepping only because we want to be more accurate with respect to Jacobian with the gap function. We will update the contact gap and the Jacobian. So we use for this I think we use only 2 time steps, and you see the deformed configurations in the time steps. And let's see how it performs under uniform refinements. So the first row is the number of elasticity doves from 13,000 to up to 300 million. And then this is the contact subspace dimension. So from 300 to about 238,000, you see it grows like a 2D problem, so times 4, because again, it's a surface. Compared to the 3D problem that it's multiplied by 8. And when I say max is the maximum dimension across all time steps, because you might change time, maybe it moved a bit, so you might change the contact subspace. This is the number of constraints, so it's related to the number of contact constraints. This is lambda, dimension of lambda. And then this is the average number of interior point iterations it took to converge. Again, average, oval, or time steps. So as you can see, it goes from 16 to 23 under 5 successive uniform refinements. And the most important, I guess, row here is the last one. So the numbers you see here, not in the bracket, is the average number of PCG, AMG, preconditional with AMGF over all time steps, over all optimization steps. So for example, this is solved 16 times for time steps times, 2 time steps times 16 optimization steps. And the average is 72. And the average goes from 72 to 150 over 5 refinements. I think this is expected growth because we also grow the number of processors with AMG. It has some growth because of the smoother change and so on. In bracket, we have this estimate of the condition number derived from this relation. So we solve it without contact. We multiply by square root of 2 approximately. And this would be the theoretical upper bound. So you see we're way below. So we're very happy to see that we did stay below the upper bound that we proved. So this is more analytical, more extensive results for the last three large meshes. So you see the upper bound is, for example, is 210 here. It's way for the 2 time steps using AMGF. And then this is what would happen if you had solved it with AMG. We capped it at 5,000 iterations because we couldn't go beyond. And this was taking about 2 days to run with AMG. Because, yeah, So moved on to a couple of more examples. This is still linear. You have a die that will be pushed towards the slab, and then it will slide on it. It's driven by the Dirichlet boundary condition on the displacement here. So the first 4 time steps, I believe, 3 time steps will be pushed down and then slide over. And you see a similar behavior in the solver from 12,000 to 300 million, and then iterations from 73 to 195, but you also see the upper bound estimate. And these are similar graphs. We did get close to the bound, and I was getting worried, but we just hit it up there. Maybe we had a sharp bound. But you can see the behavior, right? I mean, it's as soon as the constraints kick in, you see the effect. Again, this axis is like optimization steps. So last example here is linear and nonlinear elasticity. So same problem, linear elasticity, and this is solved with nonlinear elasticity, the neo-Hookean material from MFEM. You have this, actually you have two beams compressing a sphere where it has another sphere in it, or spheroid in it. It's just we model here only one octant, and we do symmetric boundary conditions on this side, and at the bottom. We needed the nonlinear to capture this buckling here and this opening of the gap, because we wouldn't get it with the linear model. And I will show here that so we solve it with six time steps, and I will show here results for the nonlinear. The linear is similar. Again, from 17 to 51 average iterations, and the same for the interior point iterations from 17 to 31, under 5 refinements. And again, similar story for each time step. There's no upper bound here because it's not unique, case changing every time step because it's nonlinear. So with respect to MFEM, there will be 2 PRs. There are 2 PRs, which are marked whipped, but maybe until Monday they will be ready for review. So one is introducing this filter solver along with AMGF solver. Filter solver because it doesn't have to be AMG plus filtering, can be any solver and plus any solver. So that's like the base class, and in here is from that we'll have the AMGF. And along with that, we'll have the contact mini up here, which introduces the interior point solver, which is going to be local in the mini-app directory. And it will provide all the examples that I gave here. Just to get a taste how it will look like, you define your elasticity operator. This will be linear or not linear. And you define this optimization problem that you will return for you, that will apply contact. Again, this is through tribal. And it will return for you the Jacobian and the gap function. You will define the solver for the subspace solve for the filtering. And the AMGF solver will define an internal AMG object, which you can have access, have public access, and set the similar AMG options you would do otherwise. And then you can define your own subspace solvers. In this one, it was a direct solver. And you have to define your transfer operator. It doesn't have to be a prolongation. You need to have this transfer the assumptions of our theory will still apply. You define your solver for each step, and you pass everything to the interior point solver, and the interior point solver will update the operator, and automatically preconditioners will be updated and everything. So to sum up, I think I convinced you that AMG had some trouble with constraints, and we successfully were able to mitigate this by using this filtering approach. And then we are very happy that our theoretical estimates were supported by the results. or the other way, maybe. And will be 2 PRs, and there is a paper which is under review, hopefully soon published. Thank you for your attention. And I'm fast. I will leave this blank.
Okay, thanks, Socrates. Very nice presentation, very impressive results. Just a very small, like, practical question. So for the contact surface in MFEM, like, how do you identify the degrees of freedom on the contact surface? Because you have to do it every time step, right?
Yes. So when the Jacobian comes out of tribal, we can see which rows are empty because it will not touch the non-contact. So
you just
we
look at the
were
closed
lucky
rows.
that this comes this way. Otherwise, we'll have to geometrically do something there, but I guess it's done in tribal. So Jacobian comes as a full size, but most of its rows are empty. So,
And in this context, I guess a follow on that is, so the contact surface, does it have to be like a simply connected domain, or can it be like a ring touching, or like, could it be like legs touching or something?
yeah.
Can be, okay.
Yeah,
so it doesn't have to be.
Can be,
Okay.
yes. Yeah.
Nice.
Yeah.
Yeah, very nice talk. I think we've discussed it before, but I want to ask, can you, instead of combining them multiplicatively, can you combine them additively? And does that remove the requirement that the elasticity solver is convergent?
The answer to the first is yes. And I tried it and it works. And it's not a surprise that it works. Theory, we haven't put it down, but I would assume that will get another bound, but I don't know. Can we remove that assumption? I don't know. I don't know if you can remove the assumption on the. Oh, I get it. As long as it's a preconditioner still, you might be able to remove it. Yes.
Yes. Right.
Yes. Yes. I would say probably yes now. Yeah.
Okay. And
Because to make it convergent, you kind of scale it, but then if you put it as a preconditioner, the scaling will automatically apply it.
Right. Yeah, that's the
Yes.
idea.
Yes.
Yeah.
Yes.
And so I noticed with the tables you present with the numbers and the numbers in the parentheses, right, there is this kind of increase, maybe a factor of 2 increase going from coarse to fine. But because you see it in the parentheses, that just comes from AMG
Yes.
on the non-contact
On the
problem.
non-contact.
Is there something better you can do for elasticity that would be?
We tried whatever is the optimal one. We tried, even the elasticity options or not. It's just, it's there. So I tried several smoothers from the available ones.
But if you have any other,
Yes.
if you have a better performing elasticity solver,
Yes.
what this tells you is that by adding filtering,
Plug
it
it in.
will work with contact.
Yes.
I'm asking about that if.
Yes. Yeah.
I have a question. So yeah, very impressive work. What kind of constraint you need for this perturbation constraint to make the filter working? I have a different constraint, but it's also similar.
What kind of constraint? I don't think it's.
So
I don't think it matters.
So we have a similar problem. It's Laplace plus low rank perturbation, and then the low rank is boundary integral. And
Yeah, I think it's gonna work.
Well, okay. Well, we try various things, but it doesn't perform very well.
Okay.
Okay. Maybe.
There was no assumption in the analytical in the theory on what kind of is. It's just it's whatever is causing you the issue. I mean, will definitely be efficient if the subspace is small. So if it's a boundary constraint.
You
Well,
have
so-
boundary constraint too, right?
Yeah.
Yeah, it's an integration.
Yeah.
Also, the low rank, we also try something like Woodbury identity,
Okay.
which will remove the low rank perturbation. With have you tried something like that?
We haven't.
You know what I'm talking about, right?
Not sure.
So, yeah, Sherman's. Yeah.
No, we haven't.
Do you think will work with low rank perturbation?
Possibly.
It depends how long.
Yeah.
So one question, you use direct solvers mumps
On the
for
subspace direct solver.
okay. So if you have like something structure that has a lot of contact relative to the volume, this might be a
This
big price to pay.
maybe it would
potentially.
get expensive. Of course, you could do. It could be. I mean, if there is big area and it's connected, it will get expensive. If you have small patches, I think you can still do multi, right?
Yeah.
This is two level. Yes. Or you could do.
Well, where are the multi-level?
Or we can do something multi-level for the contact instead of the.
Yes.
Yeah,
It's
okay.
really good.
Or you could
Yeah,
have
so-
multiple subspaces additively.
So I'm asking because a long time ago I was looking at problem like that, but the number of the constraints was close to the number of the unknowns.
Yeah.
Maybe a
That-
fraction of it, but
that will not scale in this setting unless you have a good solver specific for the subspace, right? Yes.
But the form of J, how much does that matter? Like, I know that it has to be J transpose DJ and for any J or for any J matrix?
Well, the fact that J is sparse is what allows you to isolate that to a small. If J was as sparse as K, this wouldn't.
Isn't it the dimension of J?
Dimension,
poles
yes,
to J.
but it's like most of its rows are empty. So like when you do J transpose DJ, to take that square matrix will only affect like some small square matrix. Which
So if J
which
has
is of,
like
which is of this dimension. So this dimension here, for example, in the end.
So if J is tall skinny matrix, but the entries are non-zero, it's not gonna work well?
It's gonna work. It's just gonna be expensive to the subspace is bigger, right?
You mentioned subspace is the number of non-zero rows in J. Is that right?
That's correct.
Okay, maybe 6 something.
Well, it will be as big as the rank of J. Yes.
That's the number of columns.
Yes. Yes.
It should still work.
It will still work. Yes.
I mean, that's what I was expecting.